So far we have discussed that after developing the algorithm, and analysis of algorithms, analysis result can be represented most optimally in terms of theta notations, because this is the most optimal notations where we are specifying both the upper bound as well as lower bound, and depending on the type of the problem and the algorithmic steps, different problems has different complexity. Some problems has running time theta n, some steps, some algorithms has running time theta 1. This is known as constant running time. This is called linear running time. It can be theta n square, where the running time depends on the n square, or it can be theta n to the power k, where k is greater or equal to 1, and definitely the value of k is greater or equal to 1. So this is called polynomial time running time. Some algorithms has worst algorithms that running time is theta n to the power very large value, say n to the power very large value like n to the power n, or some algorithms has theta 2 to the power n. This is exponential running time. Now let us estimate that depending on these notations, order notations, how we can compare different algorithms, because depending on the value of the input, how algorithm behaves depending on the value of n and according to different growth rates. Let us estimate for that, considering a hypothetical computers where number of instructions executed per second is 1 million. Now for smaller values of n, if n is 10, then if the algorithms has running time of theta log n, then it will take 3.3 microsecond. For linear time algorithms, it will take 10 microsecond. There is no much differences. For n log n base 2 algorithms, it will take 33 microsecond. N square 100 microsecond. This is 1 millisecond, and 2 to the power n, it is also 1 millisecond. So the difference is not much, but you understand that if the value of input is large, that is n square is 2 n square, then log n has 6.6 microsecond, n is 100 microsecond, n log n is 664 microsecond, n square 10 millisecond. N cube algorithms takes 1 second, whereas 2 to the power, that is exponential running time algorithm, that will take 4 into 10 to the power 16 years. So just imagine that what matters, that is the growth rate of algorithms, that is the number of basic steps executed per second, here assuming 1 million operations per second, and depending on the design of algorithms, the running time matters, because running time is ultimately proportional to the number of basic steps. So if we have developed an algorithms which solves the problem in log n time, then life is very good, fine. But if the same problem is solved with a higher polynomial running time or even exponential running time, though the design is very simple, but we cannot get output maybe after years or after years, you have to wait a long, so it is horrible. So from this point, it is very clear that algorithm design is very important aspect, because if we can design better algorithm which solves the problem in n log n time or log n time or linear time, then this will give the output in less time. Whereas if the solutions is exponential or higher degree polynomial, then those solutions are not at all accepted, because even for a larger input, 2-digit input or 3-digit input, the output may not be obtained at all. So that's why the analysis and design of algorithm is very important. In the next lectures, we will discuss the different design of algorithms like divide and conquer, dynamic programming, greedy, backtracking, etc., and how we can compare the different analysis results that we will discuss in successive lectures. Thank you very much.